I want to introduce someone who I think all of you know, Dave Weixelman, a longtime club member, a retired Forest Service botanist, and you've also been an amateur astronomer since you were a kid when you made your first telescope.
Seventh grade.
Seventh grade, yeah. And many of you have seen the photos that Dave posts to the groups.io list. He's posted many of the moon. He also gave a presentation, was that last year, maybe year before? Year before on landscape photography with the solar system, or I should say with the galaxy in particular, and other celestial things there as well. So he's obviously a very talented person who we're happy to have here tonight and present to us about the moon. So please welcome Dave.
Thank you, Rod, for that introduction. And wow, it's kind of timely. We're talking about the moon. What a day for the launch, Artemis 2. I hope a lot of you got to see that launch. Reminded me of the good old days in high school watching Apollo. I got that same feeling, very, very excited about it. And, but we're not talking about Apollo today. We're going to talk about observing the moon. And I've got a bunch of topics here that I've listed here to talk about. Some things about basic information, size and distance, a little bit on the theory of the moon's origin. We're going to talk about libration, which is a whole interesting topic in itself. We're talking about some of the major features on the moon, including the Maria, the craters, and the mountains. And then I've selected top observing targets that are quite famous as far as observing the moon. And so I've got 10 of those that I'll touch on. We could list a lot more. There's a lot of really interesting features on the moon to look at. Basic lunar facts. So size and distance. Many of you know that the moon is about 1/6 the size of the Earth. The diameter is approximately 2,100 miles, which for reference, that's about the straight line distance from San Francisco to Cleveland, Ohio, just to give you a little bit of perspective. And it orbits the Earth at an average distance of about 239,000 miles. Gravity is much weaker than on Earth, about 1/6 of our planet's gravity. And if you remember some of the Apollo landings, the astronauts, when they would walk on the moon, they'd actually kind of float and hop. Right? And so that you could see how light they were on the moon just by watching them on the moon. The moon's surface is marked by many features, including impact craters, mountains, and lunar maria. And the maria are large dark plains formed by ancient volcanic activity. We'll talk more about those. The moon is tidally locked to the Earth. What's that mean? Well, it means that it always shows the same face to our planet. Its orbit around the Earth matches its rotation period. And I'll demonstrate that here with some props here a little bit. So as far as the formation of the moon, the most popular theory now is the moon was formed about 4.5 billion years ago, shortly after the Earth. And most scientists today support what's called the Theia impact hypothesis. And here we have this Mars-sized body called Theia smashing into the Earth and creating a huge debris cloud in space. And that Theia collided with the Earth, creating this large debris ring, which then coalesced to form the moon. Okay, and so this graphic here at the bottom kind of summarizes that. Theia here approaching the Earth, about a Mars-sized body, that's what they speculate. And you had impact, you had a huge debris ring form around the Earth, here, if you follow the cursor. And then that debris ring coalesced into the moon. And that's a popular hypothesis because of these facts here. Based on the lunar samples, the moon's composition of certain isotopes exactly matches that of Earth, but does not match those of bodies elsewhere in the solar system. Mars rocks and for example, Mars rocks and meteorites from other parts of the solar system have different oxygen isotope compositions. So the ability of the giant impact hypothesis to predict not only the moon's composition, but also its orbital characteristics are major reasons for acceptance within the scientific community. So that's the dominant theory for lunar formation.
So in other words, all of those pieces just got attracted to each other and...
Coalesced to form the moon, yes. And if you look at the models and read some of the results from the models, they speculate that it's really a glancing blow, that Theia made more of a glancing blow than a direct impact because the moon's composition resembles our mantle very closely instead of its core. So most of the debris that coalesced was apparently made of the Earth's mantle and not much deeper than that. So that's one of the...
Is there any evidence of where that impact happened?
Pardon?
Is there any evidence where that impact happened?
I've not seen any as far as on Earth, no. It was shortly after the Earth formed, so, based on, all the disturbance since then, maybe that's difficult to ascertain. But I have not seen anything written on that. But it's interesting that they speculated it was a Mars-sized body, so it was quite large, obviously. And so, yeah, very interesting. Now, one of the offshoots of this model, or one of the confusing factors is that the crust on the near side of the moon is much shallower than the crust on the far side of the moon. And that's perplexing. So how did that happen? And some models suggest that another body collided with the moon after the moon had just formed and added its material to the far side of the moon, because the crust on the far side of the moon is over twice as deep as the crust on the near side of the moon. Interesting situation.
And what's inside the moon? What's in the core?
There's an iron core, but it's very small. And so that's why they speculate that not much of the core of the Earth or of Theia was captured by the moon. Mostly mantle material and very little iron to coalesce into a dense core. So, yeah. So that's the formation theory. So the moon is tidally locked. Well, what do we mean by that? Tidal locking occurs when a celestial body rotation period matches its orbital period around its partner. So it always maintains the same face towards the Earth. But that's not entirely true. We can see, instead of about 50% of the moon, we see about 59%. And the reason for that is because the moon wobbles a little bit as it faces the Earth. Sometimes we can see a little bit of the North Pole better, a little over the North Pole, and sometimes we can see a little bit over the South Pole. Sometimes we can see over the eastern limb a little bit more, and sometimes over the western limb a little bit more. So that's called libration. And there's two kinds of librations. One is in latitude, where we see the northern part better and sometimes the southern part better. And the reason for that is because the moon's orbit is inclined 5.2 degrees to the plane of the ecliptic. So sometimes, if you follow the cursor there, we're below the moon relative to the plane of the ecliptic. And so we see the southern zone of the moon, southern pole, better than the northern pole, okay? Where conversely, when the moon is at the other extreme, we are above the moon and we see the northern part of the moon, the North Pole, better than the South Pole. We can actually see over the North Pole just a little bit. So that's called libration and latitude. And the result of that is, as the moon moves in the sky, it sort of wobbles up and down like it's nodding to us. And it gives us a north-south movement. Okay, and that's called libration and latitude. There's another type of libration, which is libration and longitude, which is a little more involved. And I'm going to read the text here and follow along with me, and then I'm going to do a little demonstration here so you can kind of follow along. Libration of longitude refers to the apparent east-west wobble of the moon. So before we talked about north-south, now we're going to talk about east-west wobble of the moon. And this allows observers on the Earth to see slightly different portions of its surface over time. Now, a couple of things here. The moon's rotation speed on its axis is always constant. Okay, in its orbit, it's always constant. The moon's orbit around the Earth is elliptical, meaning its speed varies. And when the moon is closer to the Earth, at perigee, it moves faster than it's farther away at apogee. So the moon's rate of motion around us changes depending on whether it's at apogee or perigee. Okay? But keep in mind, the rotation about its axis is always the same. This is going to have a consequence. This difference in speed causes the moon's rotation to sometimes lead or lag behind its orbital position, resulting in libration and longitude. So let's just demonstrate that a little bit here. So what I've got here is a Earth right here, and I've got the moon with a little black dot on it, okay? Now if, let's just say, if the orbit of the moon around the Earth was perfectly circular, and the rotation of the moon always was such that the black dot stayed pointing toward the Earth, okay, then the rotation on the axis of the moon would exactly match the orbital period, because I have to turn this at a certain speed in order to keep that black dot pointed right at the Earth, okay? Just imagine that's the case. But that's not what actually happens, because when the Earth, when the moon rotates or in its orbit around the Earth, sometimes it is apogee and sometimes it's perigee. When it's farthest away, I'm going to back up a little bit, its orbital motion is slower. Okay? So let me start out with the black dot facing the Earth, but now I'm going to keep the same rate of rotation about the axis here, but I'm going to slow down the motion of the moon around the Earth. Okay, so what's going to happen? This black dot is going to start to lead and not face directly towards the Earth, right? Because my rotation about the axis is fast enough that it's sort of leading this black dot away from the Earth. Okay, so it doesn't always point to the Earth. So we can see this side of the moon a little bit better than the other side. Okay, we can peer around that limb. So that's libration and longitude, where the moon is sort of doing this to us, you know, going back and forth. Now, if it's conversely at apogee, that was apogee. At perigee, when it's very close, the moon is going very fast, but in its orbit, but the rotation speed about its axis is the same. Okay, so in that case, the black dot doesn't quite keep up with the orbital motion, and so it points off in this direction to the Earth, and so we see a different side of the moon. Okay, does that make sense?
Yeah.
Okay, so that's libration and longitude. And this fancy diagram here just kind of illustrates that. Instead, the black dot I had on the ball here is the same as these little arrows here on each of these moons. Okay, so for example, over here at apogee, when the moon is going slow, the moon's rotation leads the orbital position, and that little line there doesn't always point doesn't point directly to the Earth. Okay, whereas it did here, but now it's leading the orbital position. So anyway, what the result of that is the moon just wobbles back and forth, okay, in its orbit around the Earth. So and to sort of show that here with an image, Grimaldi is a famous dark basin on the moon, and when libration occurs, sometimes it appears very close to the edge of the moon, and sometimes it appears quite far away from the edge of the moon. So the moon has sort of rotated east-west in that position. So that's libration. And again, two types of librations, in latitude and in longitude. And if you're interested in the lunar libration and what the stage of libration is going to be as far as north, south, and east and west, there's a great NASA site called NASA SVS. And if you just Google NASA SVS moon phase and libration 2026, you can get to that URL. And it's cool because you can put in a date and it'll show you the libration of the moon. Very interesting.
What is the one rotation? How long does it take?
28 days.
Oh, that's right, 28 days.
28 days, which we're going to mention here in a little bit.
27.
Great question.
27, 23.
Yeah, it's exactly. It's a little bit less than 28. Yeah, just holler out questions if you have questions. So, yeah. Anyway, that's a website that's very handy for looking lunar libration. So a little bit about moon terminology here. There's a couple of terms here that I'd like to point out, and one is called the limb. The lunar limb is actually the edge of the moon that's visible from our Earth. Okay, that's just that simple. Here's the limb right here. Whereas the terminator is actually the line that separates day from night on the moon. So here's a waxing gibbous moon, and we'll talk about that in a little bit here. And the sun is rising on this part of the moon right here. So that's the terminator. It's basically the shadow line. Now, I mentioned lunar, perigee, and apogee. When it's at apogee, it's its farthest, and perigee is at its closest. And the difference in size is actually quite noticeable. It's 12% smaller when it's at apogee as opposed to when it's at its closest. So there's quite a big difference. Now, you may not casually notice it if you're looking at the moon, just glancing at the moon, but the 12% difference is it's pretty significant. So a big difference there between apogee and perigee. Now,
What
lunar
causes
phase.
that?
Go ahead.
The distance.
What causes that?
It's the elliptical orbit. So, one side of the ellipse, the moon is actually closer to the Earth than the other side of the ellipse. So, yeah. So that's it's closer at some points in its orbit and further at some other points in its orbit. It's not perfectly circular. Moon phases. So when we talk about moon phases, I wanted to explain how, when we talk about how old the moon is, for example, say it's 7 days old versus 3 days old or something like that. The new moon, when the moon is between the Earth and the Sun, we call that a new moon, or 0 days. Basically, that's the start of the lunar cycle. And the lunar cycle, again, is just short of 28 days long. First quarter is referred to as a 7-day-old moon. So that's 7 days. So between a new moon and first quarter is what we call a waxing crescent. Then between first quarter and a full moon, we call a waxing gibbous. And again, first quarter is 7 days old, and full moon is roughly 14 days old. Then, of course, another 7 days after the full moon, it's at last quarter, and then it goes back to new moon again. So when it's at full moon and then it's getting smaller, at least the lit portion is getting smaller as viewed from Earth, we call it a waning. And then last quarter again is right here at 14 plus 7, roughly 21 days. And then we start over at the new moon again. So that whole cycle is just short of 28 days. But anyway, when you hear lunar observers talk about the moon, sometimes they'll say, well, the crater Copernicus is best seen at about an 8-day moon. That's what they mean. So as far as the age goes. We've talked in the past in these meetings about the orbit of the moon and why the full moon doesn't always line up with the Earth's shadow. Because the moon's orbit is inclined to the plane of the ecliptic. But sometimes, once in a while, the moon does line up with the Earth and the Sun and falls within the Earth's shadow, and we get a total eclipse of the moon. Right? And this happened on March 3rd here, about a month ago. And Rod and Greg, and I were out at Washington, but it had a great evening just observing that eclipse. And this is one of the photos I took. And this was at mid-eclipse, right in the middle of totality. So yeah, and most of you know why the Earth or the moon turns red during the eclipse is because that light that's blocked by the sun is actually being refracted around the edge of the Earth and reddened by actually the Earth's atmosphere. So it's bent around, and we see the red rays as they're bent around, just like at sunset. So those red rays are hitting the moon. So bright and dark areas on the moon. So there are bright areas on the moon and there are dark areas on the moon. And you can see that with the naked eye, right? And the bright areas are known as the highlands, or mountainous areas. And they're lighter colored. Here you can see many of the lighter colored areas. They're composed of anorthosite, a rock composed primarily of calcium-rich plagioclase feldspar, which cooled quickly after the moon's formation. And for you rock hounds, the Sierra Nevada, the primary feldspar is plagioclase, which is a very light-colored mineral in the granite. And so it's interesting that we have the moon, the lighter color is given by sort of a whitish feldspar, and on the moon, just the same as the Sierra Nevada granite also is rich in plagioclase feldspar, which is light-colored. The dark areas are called maria, which are the darker regions that are often basins formed by large impacts. And so these maria are caused by large impacts that are later filled with lava. So, for example, this sea over here, which is the Sea of Crisis, Mare Crisium, was a large asteroid impact which pierced the crust, and then under the crust was magma, and the magma oozed out and flooded that basin right there. That's Mare Crisium, the Sea of Crisis. And the Maria are darker due to an iron-rich content and have lower albedo, meaning they reflect less light. So that's the story behind the bright and dark areas on the moon. And the Maria are named, they're all named, and I'm not going to go through all these names, but for example, Mare Tranquillitatis, here, Tranquillitatis is the Sea of Tranquility, and that's this sea right here. Okay, where Apollo 11 first, when they first walked on the moon, that's where they landed. In fact, pretty close to where that arrow meets the Mare right there. Here's the Mare Crisium, which I mentioned before. So yeah, those are the names of the Mare. Now, crater types. There's two very broad crater types, simple craters and complex craters. And simple craters are basically very small craters where the depth is about equal to the width from rim to rim. Generally, they're smooth in their bowl shape. However, complex craters are identified by they're much larger, and they have a central peak. They have terraced walls, and the width is much greater than the depth. And oftentimes they'll have a central mountain which forms after those impacts. So those are the two, and we'll see examples of both of those when I talk about the lunar features here later. Here's an example of a complex crater. This is Aristarchus. And you can see the terraced walls here, and you can see the central mountain there in the crater. So that's an example of a complex crater. Okay, so observing the moon. I picked out 10 features here that I enjoy viewing and are quite famous features on the moon. And we'll start with a crater called Plato. Now, some of these, several of these features that I'm going to talk about here at the beginning are on the rim of a giant asteroid impact. And that giant asteroid impact I'm outlining here by the cursor, this is Mare Imbrium, which flooded with lava right after the asteroid impacted that area. And mountains then formed around, forming the rim of Mare Imbrium. But there's some interesting features on the rim of Mare Imbrium. And one of those is the crater Plato, which is a very dark, circular crater up here on the northern part of the Imbrium basin. And here's a photo of the Plato. It's a dark, floored crater, one of the darkest areas actually on the moon, named after the Greek philosopher Plato. But it's striking in its how smooth the surface is and how dark the surface is. And it's quite a famous feature on the moon. And it's roughly 68 miles in diameter. So that's Plato on the northern rim of the Imbrium basin. Another, yeah,
When they say smooth,
relatively speaking.
relatively, I mean, relative to like Sierra Nevada, is it more like a farmer's field smooth, or is it kind of still rolling?
It's a lava field, but it's a lava field. I don't know how bouldery it is, but when you look at it through a telescope, it looks really smooth. And so that's the meaning. That's what I mean. Now, there are some small, really tiny craters on it. If you really get into high-powered viewing of the moon, and you have really high resolution with a big scope, you can see small craterlets that are scattered around. But to most telescopic views, it looks extremely smooth. And so it's got this, it's sort of known as sort of a smooth floored crater.
Are all craters on the moon impact? Are there any volcanoes? Were there any volcanoes?
From my reading, they are impact.
No volcanoes?
No volcanoes.
Why?
Because I don't know the answer to that, but I have read that the craters on the moon are impact formations.
Well, you said it was formed differently than the Earth was, right? Because it was broken off from the Earth only from mantle.
Right.
So there's no cores, there's not all the different cores.
Doesn't have a lot of iron.
The iron core is very small.
Yeah, and wouldn't that account for the volcanic activity on the Earth? Is that molten core? So since it doesn't have that, you wouldn't expect it very much, any volcanic activity.
Yeah, maybe that is related to maybe the speed at which the moon cooled, perhaps, you know. And it's, so, yeah, no, great question, great question. I don't have any answer, except that I have read that the craters are all impact formations. And all sizes, because you had asteroid impacts, large bodies which formed, for example, Mare Imbrium here, to the smallest craters on the moon. So all everything in between, all sizes. So another feature on the edge of Mare Imbrium is what's called the Bay of Rainbows, or Sinus Iridum, which is a half-circle bay up here on the northern part, again, of Mare Imbrium. And it's an interesting telescopic object because it's C-shaped, it's quite distinct, and it's pretty obvious that half of the crater was filled with the lava from Mare Imbrium. And so, yeah, it's a very distinctive feature on the moon. This is the Bay of Rainbows, and quite obvious in the telescope. Interesting feature. And another feature on the northern edge of Mare Imbrium is called the Alpine Valley. And here's a picture of the Alpine Valley I took not too long ago. And you can see it's this gash through this mountain range here on the edge of Mare Imbrium. And it's hypothesized that it's just it's a geologic feature, we call it Robin, which is a block of land that dropped along fault lines and was flooded with magma from Mare Imbrium, nearby Mare Imbrium. So it's a very distinctive feature on the moon. And as far as telescopically, it's really a challenge to see this rill running right through the middle of the Alpine Valley here. It's very difficult to see. It takes a large telescope, but it's a real challenge to observe. The Apennine Mountains is a mountain range, again, formed by the Imbrium impact, and that's the mountain range right here. We're going down sort of south now from the Alpine Valley, and here's a picture of the Apennine mountain chain right here. And one of the interesting things about the Apennine mountain range is here's another picture of the Apennine mountain range again. Here's Mare Imbrium right here, and right about here where the cursor is where Apollo 15 landed. And Hadley Rill is a huge gully there that was probably once lava filled, but it's right in here, and Apollo 15 landed right beside that. And telescopically, it's an interesting challenge to try to see Hadley Rill. So that's a photo of the Apennine Mountains. And next, I'm going to highlight the crater Copernicus, which is a famous crater here. And right here, it has a bright splash pattern, a bright ray pattern. So the craters that are brightly rayed like this, have a nice ray pattern here, are the newer craters, because that's fresh ejecta and hasn't been worn down by micrometeor impacts over a very long time. So this is the crater Copernicus. It is a complex crater named after the astronomer Nicholas Copernicus. It has a bright ray system that extends out to about 500 miles, so a long ways. And it's roughly 58 miles in diameter. It's the classic complex crater with a mountain in the center and terraced walls. But it has a wonderful ray pattern around it. And that's just south of the Apennine Mountains. And Sea of Crisis is another feature that's famous on the moon. That's this large lava-filled basin over here that I talked about earlier. In Latin, it's Mare Crisium. And so here's a picture of Mare Crisium near the limb of the moon. 345 miles wide, so it's a very large impact basin that was flooded by lava. You can actually see Mare Crisium with the naked eye, and certainly in binoculars. So it's actually pretty noticeable to the naked eye once you learn it. Now, a couple of small craters here on a Mare just south of Mare Crisium are very interesting. This is Messier and Messier A. And here's a close-up from a NASA satellite photo. And what's interesting about these craters is it's conjectured that the impactor came in at a very shallow angle, gouged out this elliptical crater here, and then skipped and then formed another crater here. And then the ejecta from those collisions then sprayed off this way. So it came in at a very low angle. So that's the Messier A and B craters on the moon. Very interesting situation. That's pretty uncommon. You usually don't see this. And I've got a picture here of the Messier craters and the ray, the double ray that goes off this way. You can see on this picture. And that's best seen at a high illumination moon. So if there's low illumination, you don't see these rays very well. But near full moon or gibbous moon, these rays really stand out. So that's quite an interesting feature. And then the straight wall is a fault line on the moon. It's a famous telescopic feature. And so now we're going to bounce over from Messier, clear over to here. And this straight wall I photographed a couple of weeks ago, it's this thin black line right here that you can see right there where the cursor is. Hopefully you can see that. And here's a close-up from a NASA orbiter. And you can see the fault line right here. The shadow of the fault line stretches about 62 miles. And height ranges from roughly 700 to 900 feet. And a day or two after first quarter, which is about 8 or 9 day old moon, this black line shows up very well. And Tycho is a famous crater on the southern part of the moon, and it's famous partly because it has a tremendous ray system here that spreads out in all directions. It's a very young crater. And they say the age is about 108 million years ago, which is very young for a crater. But here's Tycho right here with its central peak, its terraced walls. And you can see some of the ejecta here, but on fairly well, but not as well as a photo here that I got from Ballard Bear, who's a longtime member of this club. And anyway, Ballard has a fantastic photo of Tycho here, which is by the cursor, and the tremendous ray system that emanates from this crater. It's quite prominent that way. And again, those rays can travel some 900 miles across the moon. It's a very fresh crater. And the fact that you can tell it's a young crater simply by the fact that the ejecta lie over other craters, showing that that ejecta is younger than those craters. And finally, I'm highlighting a crater called Clavius, which is in the southern area of the moon, just below Tycho. There's Clavius right here. It's one of the largest craters on the near side of the moon, and spans about 143 miles in diameter. And what's interesting also about Clavius is that NASA's Stratospheric Observatory found H2O, frozen H2O, within the crater's floor. And that was one of the first signs of water ice on the moon, which has led to finding more water ice. But this was one of the first examples of it. Clavius has an interesting ring or arc of smaller craters, craterlets on the floor. It's quite distinctive that way. So that's Clavius, just south of Tycho here. And this is the lunar South Pole vicinity. And I show this because this region is going to be gaining a lot of attention in the years to come. Here's Clavius again, and we're south of Clavius, and the South Pole is just about where my cursor is. And when the lunar libration happens to show the South Pole really well, you can see the landing sites that are projected for Artemis 3 or 4, whichever one is going to land, Artemis 4 perhaps. And the U.S., as well as China, are looking at these sites for landing on the moon, partly because there's been water ice found on those permanently shadowed craters at the south end of the moon. And there's some mountain areas and plateaus which would lend themselves to landing right near those shadowed craters, right near all that water ice. So that's why it's gaining so much attention. So anyway, that's why I showed this photo. It's the lunar South Pole. And so, just to wrap up, hopefully you've learned a few features on the moon, maybe that you didn't know about, and a little bit about the history. And with that slide, that's all I have.
Thank you.
Any questions? Questions?
How wide is the zone of safe landing for lunar landings on that, what would be the Terminator zone, if you call it?
You mean about the South Pole?
Well, anywhere on the circumference of the moon, between where the sun hits and where the sun doesn't get, there's a narrow band where it's safe to land lunar landings. Otherwise, they burn up or freeze. Is that right?
Apollo 11 landed in a sunlit part of Sea of Tranquility, so the sun was fairly high. So I'm not sure I follow. You're saying there's a narrow zone where we can land right there at the terminator. Okay.
So there's part of the moon that's always facing the sun, so it's too hot for them to land there.
It's not always facing the sun, no.
Around, yeah,
Because the moon does rotate on its axis.
Yeah.
by 20 days, this gravity
28 days.
stays, this slight phase difference, yeah.
But you're right, the temperature extremes are intense,
Yeah.
very intense.
It's a long, yeah.
They always land in daylight just in case something goes wrong. They
Yeah.
want to sunlight.
Now, what's interesting about some of those South Pole landing locations that they're scoping out is that some of those plateaus receive light continuously. And so they're never really in the dark. So the solar panels obviously need that sunlight to keep powering. In fact, some of those mountains are over 16,000 feet high in the South Pole, and they receive continual sunlight, which means power, right? But the water ice is just below them on the slopes of those craters, which is important. So there's several advantages to landing there. So,
Well, thank you, I learned a lot, Dave, a lot about the moon. Thank you, Dave.
there's so much that we could talk about with the moon. I mean, we could just spend 2 hours on any of these topics. So I kind of skimmed over everything.
Dave, I seem to have a memory back in my previous life, I think, that the symbiotic relationship between the Earth and the Moon, that if the Moon wasn't there, the Earth would not be as very stable. Does it contribute to the stability of our axis? Any information on that you recall?
I haven't read that, so I don't know. I don't know.
I have read that. I don't know any details, but I have read that, the Earth and the Moon are unusual. Most planets don't have moons that are so relatively large in comparison to their own size. We're very unusual that we have a very large moon. And I've read the same thing, Jerry, that does contribute to the stability, though I couldn't tell you the details of that.
But I think the other point was that the biology of our planet was helped along by the tidal actions associated with that. And that created a lot of the potential for life, is belief. There's no proven factor on it yet,
Right.
but there's a lot of theory associated with that.
Interesting.
Yeah, it's very
Yeah. I sort of dug into some of that lunar formation theory stuff with Thea and all that, and that's fascinating to run the models. But that's the leading theory. It's not without controversy, but that's the leading theory. I just thought that was very interesting.
Someone told me that when you look at the moon, that it's really always the same size, but when it's low on the horizon, it looks gigantic, and when it's up in the sky, it looks much smaller. Is it true that it's actually the same size?
It's true because it's an illusion. So the moon illusion is famous, and you're right, it does look differently. And from what I've read, that's because your mind, your eye, is comparing the moon to the surrounding terrestrial features, which makes it larger, appear larger. But if you block out all those terrestrial features, the moon will shrink. Try that sometime. If you see it big and you go, wow, that's really a big moon. If you can block out the terrestrial features, it literally will shrink in your eyes. So
It has to do with perspective. When it's low, you have something to compare it to. When it's
exactly.
high, you don't have anything to
Exactly.
compare it to.
That's my understanding. But I have tried that.
You have
and
tried
it
it,
works.
and it
I mean, it
works.
works. The moon just gets smaller.
It's magic.
It's magic.
They say a way to also observe that illusion is when the moon is high in the sky, hold your thumb up and compare the size of your thumb to the moon. It's usually about the size of your thumb, and then when it's down on the horizon, do the same thing, and you will see that it's the same size.
Exactly. Yeah, that's a great, yeah, I remember that trick. Yeah, that's great.
So whether it's at apogee or perigee doesn't change our relationship to how we see its size.
Well, it does, but it takes a lot of experience and/or imagination to see the difference, right? And the casual, if you look at it casually, you may not know. But if you look, 12% is significant. Okay, but if you look it up, that will bias you. But sometimes when I go out, I think, wow, that looks kind of big, and anyway, but 12% is significant.
I wouldn't recommend a book. There's a few years ago, there's this book, actually I think it's 2 or 3 books together, 3 volumes called Luna Cognita. This guy took him years and years to write this book. It talks all about the history of how humans observe the moon, talks about all the features, and it has a day-by-day guide, essentially, during that 28-day cycle of the best things to look at for each day. It's a great book.
Yeah, there's so many features here that I didn't mention. Fault
Yeah.
lines, interesting craters, and that type of thing. So I just picked 10. But,
And I think Dave alluded to this, but the cool thing is that as that shadow line goes across, you see different things highlighted, and it's always different every night.
It's different every night, yeah.
You don't happen to have a picture of the famous cross that you have to be at
Oh,
the right
lunar
time?
X,
Yeah, the lunar X.
Yeah, lunar X, I do not.
Yeah. That's always an impressive one.
It is, yes, very, yes. Yeah, and I remember in high school trying to see the Apollo 11 landing site because they really popularized that vicinity and the craters that Neil Armstrong was focusing in on as he was landing. And I had a telescope, an 8-inch reflector in my backyard, and I was trying to see all those little craters, but of course it didn't have the resolution. But I was excited and I thought, oh, maybe I can see this. So anyway, that was cool because I was trying to relive Neil's landing view as he was coming down. But of course, there was no chance.
You bring up an interesting point. Earlier, you were talking about the flatness of the Mars. And if you can remember back to or have watched the videos that are available on YouTube, watching Apollo 11, the lander come in and the boulders that are there. And yet you look at it, a picture of the moon, and it looks flat like a piece of paper. And so it's all your perspective of distance that shrinks that obvious flatness. I mean, if you took the moon and shrunk it down to a ball of the demonstrated the size you have up here, it looks perfectly smooth. But when you blow it up, these ridges are, you said southern ones are something like, the mountains
16
are
to 20,000 feet.
Yeah, and yet they look like little ripples on a beachfront.
Right.
Since one side of the moon is dark and very cold, and it's thicker than the other side, do they have pictures of impacts on that side?
They do. Now just recall that the dark side of there's no dark side of the moon because the moon is lit up evenly by the sun, although as it rotates around the Earth. It's just that from the Earth's perspective, we only see the near side. But the far side is also illuminated by the sun from time to time, just like the near side. Okay?
Oh, okay.
Pink Floyd was just, I don't know what, anyways, there's no dark side. Right, so it's a neat thought, but it's.
The whole thing is
So, yeah, it receives light just like,
Oh,
now there are craters, like I mentioned, on the poles that are deep enough and that are shadowed all the time and never see the sun. And so that's where the water ice is apparently.
How
So-
deep are they?
Thousands of feet. So I don't know exactly. But yeah, thousands of feet deep, so.
And the reason there's so many more impacts there than we notice on the Earth is just because there's less atmosphere? Just so the asteroids don't burn up as often, or what? Why is it so many?
What I've read is, now recall that the crust is much thicker on the far side. And so those craters, when they impacted the moon, the lava did not ooze up and flood like it did on the near side. So the near side was flooded with magma and lava, which destroyed a lot of the craters that were forming. See what I'm saying? And so from what I've read, it's that lava that boiled up from under the crust and covered those large areas and hid a lot of the impact features. Whereas the far side does not have that. The lava never came up through the crust. And so those craters are preserved.
I think the question was about compared to the Earth.
Compared to the Earth?
Oh.
Yeah.
Because there's so much less atmosphere, I assume that
Yeah,
asteroids and meteors, they aren't burning up
right,
like they would, we have a natural protection.
right.
And
Right.
also we have weather
No,
and stuff
the
that
difference
doesn't-
is that the Earth is much larger, and so it is more tectonically active. So its crust is continually renewed through
That's
geologic
right.
time.
Yeah.
So all the older craters are gone. They've been subducted somewhere.
And we have oceans too.
But can you imagine witnessing that impact of Theia on the Earth to form the moon? And if you just would have had a front row seat of that, wow.
Right. I'm trying to imagine just like the view from the Earth when like some of those giant craters got formed on the moon. Those impacts must have been spectacular too. Which does bring up another point. There are observers, amateur observers, who view the moon and they see flashes on the moon when there are impacts on the moon. That happens regularly.
So the guess is when Theia hit, there was no life on Earth at that point. It wasn't somebody
4.5
Afterwards, there were
4.5 billion years ago, I don't think so. Yeah.
I don't think so.
Question, Bill?
A little bit of background, how little we knew in the early days of the space race. At JPL, they were getting the software ready to go for the Ranger to land, this is before the Apollo. They discovered that if they came in on sort of the edge of the moon, they couldn't land, they'd go off into space in a hyperbolic trajectory. And I think that's probably why when you find a land men, you put them in orbit first. And the second thing was when Ranger finally was going to hit the moon, it hit the moon a minute later than predicted. They didn't know where the moon was. The ephemerides was mostly from astrology, and also amateurs who were timing the occulting of stars by the moon. And so they began to have to radar range the moon. And before Apollo, well, there would have been a big problem. And then they formed a new, what's called the ephemerides. And then they took that information and began to range all of the planets in the solar system to get more accurate ephemerides, positions. And Tony Finnerty's brother was very much involved with that at JPL, and I don't know if Tony wants to mention any of that.
I'm not, he wasn't so directly involved in that, but he was aware of a lot of stuff going on around him.
Yeah.
For example, why some spacecraft missed their planet or cratered into their planet, which had to do with things like mixing up metric units and English units. And that was a crater job on Mars with one of those spacecraft.
Any final questions for
Questions?
Dave?
Dave, is there any evidence of recent activity of asteroids hitting the moon? I mean, like within the last few thousand years or a few hundred years? I mean, or is that activity seems to have waned?
It's waned, but Rod pointed out that some amateur astronomers once in a while will see a bright flash on the moon, and something hit the moon. Right, and so it was a small meteorite or a small object, but it's still happening, but it's, like you said, the large objects have waned billions of years ago.
I know in the solar system history, there were these called bombardment periods when there were large numbers of asteroids essentially while things were getting settled out. And those are far in the past at this point.
Well, if there are no more questions, thank you all very much.
All right.